Okay, so we have a little bit of practice talking about how to move around multivariable functions and what multivariable Taylor's theorem can be used for, and how to take limits appropriately. And now we're going to go in and prove at least one of these. I'll sketch the proof for Stokes' theorem, I think, and we'll do the divergence theorem or Gauss's theorem. But first, a little bit of kind of philosophy is really what these are, Gauss and divergence, Gauss, divergence, or Stokes. They're kind of the fundamental theorems of vector calculus in the sense that they relate endpoints to internal behavior of functions. So as a reminder, the fundamental theorem of single variable calculus is basically the relationship in between integrals and derivatives. So the definite integral of some function can be expressed just by evaluating a different function at its endpoints. And the relationship in between the function I got to integrate, which sounds tough, and the function I just have to evaluate at its endpoints is derivative. So basically, derivatives undo integrals, integrals undo derivatives. And the way that you visualize that essentially is if I want to get from here to here, I want to get from here to here. One way I could do that is by taking a little piece of slope and then multiplying by a little piece of delta x. So that's df dx evaluated at that first x, so we'll call that x naught. And then I multiply that by that slope, and it gets me to here. And then I do that again, and I do that again, and I do that again, and I do that again. And the aggregate little steps that I take along this function by thinking about its slope and the small amount that I walk will get me from point A to point B. So writing that out, you get essentially a Riemann sum. So I got to take, so let's say that we break this up into n pieces of delta x each to get from A to B. So we'll leave off the limit sum. So I take f and I look at each xk, and then f prime, its derivative. So the prime in single variable calculus is just slang for df dx, delta x. And then what I have to do is I've got to add them all up. K goes from, whatever, 1 to n. Okay, so this is an approximation of how I get from A to B. Right? So the difference in between A and B, that's FB minus FA. And if I want to make this exact, what of course I need to do is take a limit sum. So limit as n goes to infinity and delta x goes to 0. That's a really terrible looking infinity, and that's better. And then what I can do is I can make that exact. Right? So that's the fundamental theorem of calculus, but the important part is that it relates end behavior to endpoints to all sorts of potentially complicated stuff going on inside. In fact, I could come up with a different function, and this is maybe the thing that you hadn't spent too much time being amazed by. And the behavior of all of these functions, if they have the same endpoints, they'll have the same integral, right? So all of these have the same area under the curve in between those 2 points. Okay? So this will have some really neat consequences for a bunch of vector fields that we care about in physics. Okay. So this thing has 2 names, Gauss's theorem. Also known as the divergence theorem. Not Gauss's law, but it's essentially Gauss's law. So I have a vector function A, a vector field. So in 3D, this would be R3 to R3. And its intellectual content is this. So let's say that I have a volume. So imagine this is this volume of stuff, V, right? And then I have the surface that contains it, so the closed surface S. So this is the closed surface S that bounds the volume V. So S is the surface of V. Essentially what this is saying, whoops, really important. Essentially what this is saying is that if I leave the volume, I have to go through the surface. Completely astonishing, just totally mind-blowing stuff. This is really important. From a practical standpoint, what it lets you do is, depending on which one of these is easier, you can potentially do a different integral. So maybe this dot product is easier on the vector function, or maybe the surface has a high degree of symmetry. This is usually how you see Gauss's law, which is Gauss's theorem. But I'm going to blow this up and imagine that I calculus this, which means chop it up into little bits. So just like we do here, but now I have a volume to chop up. And imagine that I chop up the volume into a tremendously large number of tiny little boxes, right? And we're going to take the limit of those as it goes to, 0. And let me just focus on 2 of these boxes. That's essentially how the proof is going to go. So I've got some vector stuff coming out of this box. Where's it going to go? It's going to go into this box. So on a differential level, just like every time I go up, I got to go down in the fundamental theorem of calculus, every vector that leaves, all the flux that leaves one box will go into the adjacent box until I get to the surface. So for a vector field that doesn't have, for instance, like an infinite divergence, so source or sink or something like that. So really all this is saying in some sense is like we're conserving. If there's flux out of this, it goes into that. And the place where that conservation stops is at the surface. So that's kind of the heart of what the divergence theorem is. So to prove it in our kind of sketchy, proofy kind of way, we'll attack the surface side because that's easier. I don't know if it's actually easier, but that's what's in the notes. So let's express this. So we got the closed surface integral. So actually we'll do this. Just so I don't have to write the limit sum, we'll say approximately equal. So I'm going to chop this up into some number of internal surfaces. So imagine that SK might be one of these. So that might be SK, and I'm cutting this up into n individual pieces. So in fact, that would be an equal sign, but we'll just leave it for there. So once we've expressed this as not one total surface, but cutting it up into a whole bunch of smaller internal surfaces, the rest is honestly just like limit gymnastics. So we have this, we're going to cut this into n smaller pieces, and then we're going to use our definition of what this surface integral is from the last video. I told you those would be useful. So what is that? Well, E sigma. So haven't done anything yet. We just introduced volume above, volume below, but you can see where we're going with this. Remember all those definitions of fundamental definition of divergence, gradient, and curl, we had a volume in the basement and something that looked like this upstairs. So basically just kind of pushing things around until they look like that. And then now just take the limit as the number of these things goes to infinity, and the size of each of these individual boxes goes to 0. So I'll actually do some outside. Okay, this is the thing. And honestly, the proof of this is less important than the fact that it exists. Don't want a dot. Okay, this, flip 2 pages, 3 pages back in your notes, and what you'll see is that this looks a lot like a definition of a divergence. So the definition of the divergence of a vector function, the limit form, is this. Where this is volume, I was calling it tau before. It's v here because we're picking a for the vector function. So here, I got it, and I can replace this with the divergence, and that is the miracle of Gauss's law. So again, the content, the intellectual content of it, what it says about vectors leaving one box need to go into the adjacent box only until you get to the surface, that's going to be the most important part. And that's what we'll talk about probably in lecture about Stokes' theorem, which is the same sort of argument, but easier to draw, so we'll do it in class because that's just a 2D to 1D thing. Okay, so by definition, this limit is gradient, but we still have a sum. So we still have the sum as n goes to infinity, and delta vk goes to 0. But now we can call these divergences instead of this stuff, okay? But what this is the divergence through the kth box. And that's worth drawing after I do the last step. So this is the integral over the volume. By definition, dv or d tau, we'll call it d tau because it's now differential. So this, drawing our volume again, so this is vk, and its neighbor might be like vk plus 1, depending on how you want to do the counting, vk plus 1. So this would be the divergence, so the divergence within that box. So delta a dot, del dot a. Okay. And you would evaluate this, so what on earth does this mean? Because we're taking a limit sum, you would evaluate this in the same way that we evaluated the expression for the gradient when we proved that those two forms, the limit form and the partial derivative form, were equal. So this you would just use Taylor's theorem or something because we haven't taken the limit sum yet. Okay. So that is Gauss's law. And basically the flow through the surface, this is worth writing, I think. Flow through the surface is the sum of all of the sources of stuff within the surface. I'll write it the way I said it. So this is the flow out of or into the surface, and this is the sum of all of the spreading out sources or sinks within the surface. So remember what the divergence means. It tells you I have a source or a sink, if it's positive or negative. Okay. And then, astonishing fact is that the most important example of Gauss's theorem is Gauss's law. So I'll just write that with the terminology that you're used to. Because it does show up in a slightly different way. So Gauss's law of electrostatics, just to be super clear about it, says integral E dot dA equals Q enclosed over epsilon naught. So clearly we have this term here. What is that, and what does that have to do with volume integral? So what is the volume integral of that gives me the charge enclosed? Well, I can integrate up the charge density. And then voila, I have this. And then what I can do is express the charge density as a divergence of sources or sinks if I wanted to. But this is how the volume integral shows up. So this is the more explicit connection in between the Gauss's law that you've seen many times before, and then Gauss's theorem. I almost forgot the punchline. So this we've turned into something that looks a lot like Gauss's theorem, or the divergence theorem, but there's an implication here. And in fact, there's a second form of Gauss's law that you just read off of the relationship in between the two of these. So we've got the volume integral part, we've got a divergence. I don't see a divergence. And then we've got this surface integral with A. So if I compare this form and this form, I'm left with the implication that the divergence of A is the thing inside the volume integral. So the divergence of E has got to be equal to rho of E naught. So this is actually the differential form of Gauss's law of electrostatics, which means that if you find an electric field that has a positive divergence, you are sitting inside of a region of positively charged stuff. And if you find a region of the electric field with a negative divergence, you're sitting in a region of space that has a negative charge density. So if you're in the middle of free space with no charge density, then this should vanish. That should vanish because that vanishes. So this is also Gauss's law. Really nice form of it too, because differential calculus is always easier.